All right, we're going to look at how to find some areas and volumes using integrals. The volumes are going to be, for this video, solids of revolution. And we're going to look at a few here. This is an introductory video. So if you look at the problem here, we've got R, this region right here, is bounded by the y-axis. The graph f of x equals square root of x plus 2, that's here. And the graph g of x equals x, that's this graph here. So the area is easy enough. We want the area of region R. We're going to start with that on this video, and then in the next few videos in this playlist I'm going to make, we're going to look at some volumes of solids of revolution, and then after that I may extend this and have some solids of another type as well with certain shaped cross sections. Those are tough to visualize, so I'll use Desmos 3D to help with some of that. Maybe some other tools too when I get there. So let's get into it. This first video, we're just going to look at the area. This will be nice and quick and not too bad. To get the area of region R, we just want to visualize those little rectangles that we do when we do an integral, right? Picture that Riemann sum and picture the little rectangles going all the way across. So, you have your first rectangle maybe here, and second rectangle maybe here, and your rectangle here. And what I'm focusing on over here is the ith subinterval, the ith rectangle. And it's always good, the reason I bring this up, you might know how to find the area without thinking about all this, but it's good to think about this because when you start doing the 3D volumes, or finding surface areas or anything like that, it's very, very useful to think about that ith subinterval, that like kind of arbitrary subinterval that could represent any of the subintervals. If you can picture what that is doing, then you can build your integral for all of these problems. Okay? So as far as finding the area of region R, we're just integrating the height of these rectangles, right, times the infinitesimal width, which of course is just going to be dx. So we're going to integrate, we're going to have a dx there for the width, and then we need to represent the height. And the height of that rectangle is just the distance between this top curve and this bottom curve for our boundaries. And our top curve is f of x, and our bottom curve is g of x. So we just really need to take f of x minus g of x to get that distance between them, to get the height of that rectangle. So this is f minus g. So that's what I'm going to integrate, f of x minus g of x. And where do we integrate it? Well, we're going to integrate it from the left end of region R, which is 0, over to the right end of region R, which you can tell from the graph here is 4. It says 4 there that I just covered. But how do we know? Well, if we didn't know that, you'd need to find that intersection point, right? You'd have to set f and g equal and solve. So I'm going to show that work. I'm going to say square root of x plus 2 equals x, and I'm going to solve. Which, to do that, I want to get rid of that square root. So I'm going to isolate the square root. I'm going to square both sides. So when we square that, we're going to get x on the left side, and on the right side, you get x minus 2 quantity squared, which is x squared minus 4x plus 4. And then we're going to bring the x over, so we're going to have x squared minus 5x plus 4 equals 0 when you subtract the x over. And then you can actually factor, you get x minus 4, x minus 1 equals 0, so x equals 4 or x equals 1. X equals 1 is an extraneous solution here. It's happening because we squared both sides with that square root, and what would happen is if you continued this, the parabola that is f of x equals the square root of x plus 2, if you continued the other half of that, then the negative of that, it would intersect g at 1. That's why we're getting 1. It's an extraneous solution that comes up because when you square that square root, you don't know which half you had anymore. Anyway, x equals 4 is the solution that we wanted. So from 0 to 4 is what we're looking at. They did not intersect at 0, right? We have 0 as a boundary because our region is bounded by the y-axis. So even if we weren't given the graph we could find it by graphing these curves and the y-axis and realizing R has to be this region here. All right, so we're just going to integrate f of x minus g of x from 0 to 4. So that's, let me write it out. It's the integral of f of x, which is square root of x plus 2, and then minus g of x, which is minus x dx from 0 to 4. And when you're integrating square root of x, you want to think of it as x to the 1/2. In fact, I'm going to rewrite it right now instead of rewriting the whole thing, x to the 1/2, because you're going to use the power rule. So what we get is 2/3 x to the 3/2, right? Add 1 to the power, divide by the new power. Since it's a fraction, just multiply by the reciprocal. Plus 2x minus 1/2 x squared. Okay? And we're going to evaluate that from 0 to 4. And if we plug in 4, we get 2/3 times 4 to the 3/2 power. I'll just write it this way first. Plus 2 times 4 minus 1/2 times 4 squared. And then when we plug in 0, all of those are just going to be 0, right? They all are just power functions on x. 0 to any power is 0. So there we have that. And except 0 to the 0 power, that's, that's a different thing. Anyway, not relevant here, but it's 1, depending on who you ask, though. Anyway, if we take 4 to the 3/2 power, do the square root first, right? So square root of 4 is 2. 2 cubed is 8. So we're going to have 2/3 times 8, which is 16/3, plus 8, and then minus half of 16, so minus 8. Hey, those cancel, and so we just get 16/3 is our answer, or 5 1/3 if you like. All right, so that's it for this first video. That's the area of region R. In the next video, we'll be looking at the volume when you revolve R about the x-axis.